started in section 6.1. So we're jumping pretty far into chapter 8 here. And we are introducing what are called rational functions. So we're going to start with the definition of a rational function. A rational function is one that can be written as a quotient. F of x equals p of x over q of x, where p of x and q of x are both polynomial expressions. The denominator polynomial cannot equal the constant 0. Okay, so a rational function is just like a rational number. A rational number is a number that can be written as a fraction. A rational function is a function that can be written as a fraction. That's why they say here it's a quotient, right? Quotient is the answer you get when you divide. Well, fraction is like dividing. This rational function just takes on the form p of x over q of x. So what they're saying is the numerator, the top, p of x, is a function, and the denominator, the bottom, q of x, is a function. So in a sense, we're creating a function that is made up of two other functions as a fraction. Alright, so there are a couple other definitions that we need to make sure we know. A vertical asymptote is an imaginary vertical line on a graph where the function is undefined, meaning it doesn't exist. And the vertical asymptote will always have an equation, x equals a, where a is some number. So it will be x equals some constant. And the other term that we have to define is a horizontal asymptote. And it is an imaginary horizontal line on a graph where the function is undefined. And a horizontal asymptote will always have the equation y equals a, again where a is a constant. Okay, so we're going to take a look at what we're going to consider the parent function, the parent rational function. And now we just defined a rational function as a polynomial over a polynomial. Well, this parent function has just about the simplest polynomial in the numerator, the number 1, and it has the next simplest polynomial, x, in the denominator. And we can see the graph of f of x equals 1 over x over here on the right. And we're going to use this graph to identify some key characteristics. We're going to start with our asymptotes. We just defined the asymptotes as imaginary lines where the graph is undefined, meaning it doesn't exist. Well, if you look at this graph over here on the right, if you go right down the y-axis, you'll notice that the graph, the red graph, never touches that asymptote, right? Now it looks like, let's take a closer look, it looks like down here that graph, if we kept going down, it might eventually touch that green dotted line, but we find out that it actually doesn't. If we were to graph this on the calculator and trace the points down, 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 they would get closer and closer to that green dotted line, but they would never actually touch. Right? Meaning, x would never actually equal 0. If we look up here, same thing. This graph will get closer and closer and closer to x equals 0, but it will never actually equal it. Then let's take a look at our horizontal asymptote, which is right here. Again, it looks like the graph would eventually touch if we kept going here, but in fact it doesn't. It'll get very, very close, but never touch it. And the same thing is happening here. It'll get very, very close to that asymptote, but it will never actually touch it because at these asymptotes, the graph is undefined. It doesn't exist. Now we can write equations for these asymptotes, as we talked about on the previous page. This vertical asymptote on the y-axis would have the equation of a vertical line at x equals 0. And the horizontal asymptote that is on the x-axis would have the equation y equals 0. Another characteristic that I want to point out in this parent function is these points that they've identified for us right here and right here. So in this parent function, you'll notice that this point is at the point 1, 1, right? 1, 1. And this point is at the point -1, -1. That will be important because we will use those points to determine dilations in graphs. Just like we used with a parabola, we said you could go over 1 and up 1, but if it wasn't over 1 and up 1, then there must have been some sort of dilation. Well, these will be our key points to determine dilations. And what we're going to do now is we're going to graph some different rational functions. And we're doing this so that we can learn the different transformations. Okay? We're going to start with y equals 1 over x, which we've already introduced ourselves to. We know that we're calling this the parent function. So go into your y equals and just type in 1 divided by x. And then do zoom 6 for the standard 10 by 10 window. And while that looks very different from the graph that we just looked at because it's in black and white, it is the same graph from the previous slide. Now, on the calculator, your graph may look like it sort of disappears, right? These curves look like they don't continue on. Well, they do continue on. They just get so close to the horizontal and vertical axis that the calculator has no way to show you that it's getting really close, but it's not actually touching. Now, the one thing that we can do to verify this is if we hit the trace button and we start to trace along our curve. See the asterisk come down there? And it goes along the curve. And you can see my x number is getting bigger and my y number is getting smaller and smaller and smaller. Well, if I just keep going to the point where it looks like the graph disappears, it actually doesn't. You can see my cursor is still going, right? And so that kind of verifies that the graph is there. The calculator just doesn't have a way to show you that it's still there. Right, so there's our parent function. Now what we're going to do is we're going to graph some of these others and compare it to the parent function to see what transformation has happened. So let's go back to our y equals. We're going to leave 1 over x in our y1. And now let's type in our second function here. Y equals -1 over x. So type negative, but make sure you put your 1 over x in parentheses so that we're telling the calculator that the whole thing's negative. And now let's graph it. You have to pay close attention when you hit the graph button because it's going to graph it pretty quickly. But we want to compare the parent functions to our new function. Well, there it is. It did it pretty quickly, right? So we see in our graph that we now have a vertical reflection. What was up top has flipped down to the bottom. What was on the bottom has now flipped up to the top. And this goes right along with what we learned whenever we talked about vertical reflections with quadratics and other functions already. All right, let's go down to our next equation here. Y equals 3 times 1 over x. So let's go back to our y equals. We'll leave 1 over x in y1, but let's change y2 to 3 times 1 over x. Notice I'm using the parentheses around the 1 over x. And now let's graph it and see how it compares to the original parent function. So there's the parent. Here comes our new graph. All right, so looking at it initially, we can see that our curves have changed, right? And the question is, how have they changed? So the 3 out in front of the 1 over x has given us a vertical dilation, and we can confirm this by doing some tracing on the graph. So let's go trace. Now notice that we're on the first equation, y1 here. And remember we said if we typed in 1 for x, we have the point 1, 1. If we type in -1, we have the point -1, -1, right? Those are our like key points that we're going to use for dilations. Well, let's go to the other graph, y2 now, and let's type in 1 for x and see what y value we get. 3. So the point 1, 1 has changed to the point 1, 3. Let's type in negative 1, and we get negative 3. So the point negative 1 has changed to negative 1, negative 3. This is showing us that there's been a vertical dilation by a scale factor of 3. Now, interesting, this number 3 out in front is not just a vertical dilation, because let's do this. Remember on the parent function that 1, 1 is a key point. Well, let's type in 3 for x and see what happens. With a y value of 1. Let's type in negative 3 for x. Again, with that y value of negative 1. So not only has that parent point, 1, 1, changed to 1, 3, but it's also changed to 3, 1. Which means not only is it a vertical dilation, it's also a horizontal dilation. And so any number out in front is going to serve as both of those things. Let's go to our next equation, 1 over x plus 1. So we'll go back to our y equals. Again, leaving the parent function in there. Let's clear out y2. We're going to put in parentheses 1 divided by x, and then add 1 onto the end. And we're going to graph it and see what happens. Okay. It's a little bit hard to tell here because, again, our graph is in black and white. But we can definitely see that our curves have moved. Remember with that parent function, we had a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. Well, the vertical asymptote, it's still there, right? If I draw that dotted line in there, none of those curves, whether it's the parent function or the new function, touch that vertical line. But now let's look at our horizontal asymptote. It used to be at y equals 0. But if I put that in there, my curves are now touching that, right? Especially right here. You can look on your calculator and probably see it a lot better. But all of a sudden, what has happened is our horizontal asymptote has changed. To get a better look at this, let's go to our y equals, and let's turn off the y1 equation, that parent function. And now let's check out the graph. So by looking at this, we can see a little more clearly now that our horizontal asymptote, which used to be at x equals 0, has shifted up to x equals 1, which tells us that this plus 1 in our equation is a vertical translation. And this isn't anything new to us. We've learned throughout the course that if you tag a number onto the end of an equation, it's going to shift it up and down. Positive is up, negative is down. We are now ready to graph our last equation here. Y equals 1 over x minus 2. So let's put that in. 1 divided by, and you have to put the x minus 2 in parentheses so that the calculator reads the equation correctly. Again, let's go with the standard 10 by 10 window. Let's try to see what's happening here. So we can get a better look at this new graph if we turn off the parent function again. And let's graph it. And now you can clearly see that our curves have shifted to the right. And they've shifted to the right 2 units. And now there's a new vertical asymptote that goes right down through x equals 2. And so what that means is this x minus 2, just like we learned with quadratics, is a horizontal translation. And remember that it's a horizontal translation that is the opposite direction of the sign. So in this case, it's x minus 2, but it has translated the graph to the right 2. So we have looked at several different equations to look at several different types of transformations. And what we can conclude is that we're really not doing anything that we haven't already learned. We're just applying it to a new type of function. Okay? We've known all along that a number out in front is a vertical dilation. Well, now we know it's not only a vertical dilation, it's a horizontal dilation. And if that number out in front happens to be negative, it's a vertical reflection. We also have known for a long time that if we add or subtract the number to the x, it's going to be a horizontal translation. And then if we add x minus a number, it's going to translate it to the right. And if it's x plus a number, it's going to translate it to the left. And we also know that if we add or subtract a number on the end of the equation, it'll be a vertical translation. Positive is up, negative is down. So we're going to take a look at one final example here. Alright, so we have a rational function here, y equals 2 minus 3 over x minus 1. And we're being asked to do the following. Describe the transformation to the parent function. Well, there's going to actually be multiple transformations here. Sketch the graph. And write an equation for the horizontal and vertical asymptotes. Okay, so let's go ahead and do this. Okay, so the first thing that we're identifying here is the number 3. And we're identifying that as a dilation. By a factor of 3. Right, and as we talk, it'll be both a vertical and a horizontal dilation. And we'll get to, how that impacts the graph here in a second whenever we sketch the graph. So now we see the x minus 1. That's our horizontal translation. To the right 1 unit. Okay, so next we identify the negative in front of the fraction, and we know that that is our vertical reflection. So the last piece is the positive 2 in front. It could be tagged on to the end. They happen to write it in the front here. Don't be confused by that. That is going to be our vertical translation up to. Now we're ready to sketch the graph. So we're going to sketch the graph by starting with the asymptotes. Now remember with the parent function, 1 over x, that the asymptotes were x equals 0 and y equals 0. Well, those asymptotes are going to translate however the graph translates. So for example, we know there's a horizontal translation to the right 1 unit. So that means that our vertical asymptote is going to translate to the right 1 unit. So it's going to have the equation x equals 0. Or excuse me, x equals 1. X equals 0 would have been the parent function, right? Translated to the right one, x equals 1. We also have a vertical translation up 2. So the horizontal asymptote used to be y equals 0. Well, now it's going to shift up 2 to y equals 2. Alright, the next thing that we're going to address is the dilation. We have a horizontal and vertical dilation by a factor of 3. Now remember in the parent function, that point 1, 1 was a key point, right? So now, sort of using the intersection of the asymptotes as our new 0, 0, we're going to start from there. Instead of going over 1 and up 1, we're going to go over 1 and up 3, because there's a vertical dilation of 3. So go over 1 and up 3. We'll go 1, 2, 3. We'll have a point right about there. And we'll go to the left 1 and down 3. And we'll have a point right there. But remember, it's also a horizontal dilation. Remember, over 1, up 1? Well, now we're going to go over 3, up 1. So, over 3, up 1. We're going to have a point right about there. And to the left 3, and down 1. And we're going to have a point right about there. So next, I would just simply draw in my curves. Using those key points along with the asymptotes, I know that this graph is going to get really close to that asymptote. It's going to curve down here through there, and then it's going to get really close to that asymptote. Same thing here. It's going to get really close to that asymptote. It's going to curve down and get really close to that asymptote. We're not quite done because we have not taken care of the vertical reflection. The negative sign we said flips the graph. So, instead of this point, which we went over 1 and up 3, we're going to have to go over 1 and down 3. This point, we went over 3 and up 1, well, we need to go over 3 and down 1. Right? We're just reflecting the graph vertically. Now we can draw in the graph like that. We can get rid of this. Let's do the same thing. Let's flip the red part up. So this point here is, let's see, we went over 3 and down 1. We're going to go over 3 and up 1. So right there. At this point, we went over 1 and down 3. Well, we better go over 1 and up 3 to that point. So now we can draw in our curve. Again, the asymptotes are your guidelines, so we can now get rid of this. So that is a sketch of the graph of y equals 2 minus 3 over x minus 1.